Okay. All right. Thanks everyone for coming. Thank you, Derek, for the introduction. So I'm going to be talking about a few different sort of things here. Firstly, just show of hands, who here works in sort of the health technology space, whether that's a startup, a health provider, a payer? Yeah. Okay. So who here is familiar with? Well, firstly, who here is familiar with working with any kind of EHR in the US? Okay. Good show of hands. Who here is familiar with FHIR? FHIR. Okay, that's great. That's much better. Okay, so it's going to make the introduction a little bit easier. To give you a bit of background, my name is Elijah. I'm the product manager at InterSystems. Just a bit of a sort of speaker introduction here. So I manage our healthcare development platforms, specifically looking at our FHIR stack and standard support. I sort of work across a cross-functional team, really. So we work with clients globally, not just in the US. My background, as you might have guessed, is actually in the UK. But yeah, we've got clients everywhere in the US, South America, the Middle East, Australia, and of course throughout Europe. So, that being said, we try to find commonality between each of these regions, despite the fact that, particularly with healthcare, the regulations and the sort of data environment is radically different. With me, I've also got Duke. Duke, I'll just do a quick introduction if you want. Duke is one of our principal developers on the team. He'll be presenting on some of this as well. He's a full stack developer. He's got 8 years experience in healthcare. And then over here, we've actually got a few other members of the team who aren't presenting, but say hi to them. Extremely knowledgeable people. We've got Michael here, one of our senior devs as well. We've got Julie, who's also a product manager working on our AI healthcare stack. And we've got Lydia, one of our sort of newest joiners, who's also got good experience with some of the EHR vendors as well. So I've sort of structured this in 3 parts. The title of this is EHRs, Synthetics, and Safety. And I'm really going to treat each of these as 3 parts in the sort of developer journey. So I first want to start with talking about FHIR as an AI platform, framing this from the EHR first. So I think everyone is probably somewhat familiar with the EHR itself, right? Whenever you go for any kind of checkup, any kind of encounter, you'll typically see your clinician entering some information into some system, right? At some point, either at the point of care or somewhere down the line, the EHR itself, the EHR system is integrated with this encounter. So EHRs really act as data capture at the points of care, and specifically in the US, they're absolutely everywhere. And that's not a coincidence. The HITECH Act effectively provided incentives for meaningful use on electronic health records, which means that for more than 10 years, more than 95% of US hospitals have implemented EHRs in accordance with meaningful use. So this sort of presents sort of an interesting opportunity in terms of clinical data, right? We actually have here the richest set of clinical data ever recorded, specifically in the US, from these EHR systems. And in terms of some of the value we've seen from this, not even talking about FHIR yet, but simply from the EHR itself, we've seen extremely valuable studies on the longitudinal care records that are provided by these systems. Being able to see patient journeys over years, in some cases decades, is extremely valuable for studies across patient attrition rates, any kind of disease management, for example. There's already a good track record of using EHRs as longitudinal research sources. I specifically want to call out several of our customers at InterSystems that we sort of want to reference here, and I'll come back to some of the use cases towards the end, but we actually have a very rich ecosystem here doing exactly what I'm about to present on. So these are customers that have sort of AI-based clinical decision applications integrated directly with their EHRs. We work with healthcare providers, solution partners, even other EHRs who have sort of developed these interoperable and AI-based solutions. And really what this means is, so within the US sort of healthcare ecosystem, every EHR vendor that's achieved certification actually has to provide a set of APIs, a set of conformance certifications to allow developers to actually hook into that extremely rich ecosystem. So as we said, this is possibly this is by far the richest set of clinical data ever recorded, and there are APIs and portals to enable third-party developers to leverage that for their own usage. Again, this is mandated. So we'll talk a little bit about the specifics here, but FHIR itself is a data standard. It's becoming the standard of choice for each of these integrations. So any kind of application you want to build that's going to leverage this clinical data, this administrative data, is typically going to start using FHIR. There are integrations with previous standards as well, like CCPAs, and various IHE profiles, but increasingly FHIR is becoming the standard of choice. At this point, I think, Jeep, do you want to take it over from this slide? Or?
Yeah, sure.
Okay.
Hello, everyone. No, Elijah threw a lot at you. We're going to throw a lot more. So we'll make sure everyone's awake. Yeah. So, if we were in college, right, and we have the laptops out, and you'd be shopping at J.Crew or Facebook, right? Facebook's not too popular, right? What do they say? No one goes there anymore. It's too crowded. Okay. Yeah. Anyways, so I'll level set a bit from the developer's perspective. Where to FHIR, what problems it solve, right? Where it's going. So before, right, on the left-hand side of this diagram, right, we had other standards, right, that didn't really, meet your needs, right? And what are the needs, right? You've got EHR data. You just want to get it, right? You want to know what it looks like. You want to know how to get it. And those structures before, those data standards before FHIR had their own problem, right? That would be HL7, V3, right? CDA, right? They were monolithic. They were, in the case of V2, right? They were event-driven. So it's not really RESTful, right? It needed to be RESTful. We want to build web applications. And that's what FHIR is. FHIR is a REST-first data standard. It's modular, right? It's scalable, it's stateless. So it's really built for you to build web applications on top of EHR, right? So, and that's the genesis of FHIR, right? So that you can know what the data looks like, right? You can write the best sort of application for a given patient to view their records, and then you can point it at any backend, right? So you can go to clinic A, hospital A, you've got records there, you point it there. If they've got a FHIR server, you know what the data looks like. You can show it in an application, right, for any number of clinical uses. And then it really expanded, right? It's not just a data standard where it just describes what the data looks like. It eventually evolved to an API spec, right? So it no longer just describes what the data looks like, it's how you get the data, right? As a client requesting data, what do you have to do? And as a server serving up the data, right? What endpoints do you have to give up? And yeah, they've standardized all of that. So first it started out right with application developers. They build these applications, and the EHRs, right, they would have these vendor marketplaces where you can sell your applications, right? So you can build once and sell many, and then it snowballed right into other use cases, particularly with research, clinical research cases. And at InterSystems, right, even around 2016 or 2017, when we were developing our own care planning solution, we had a choice, right? Do we use FHIR or do we use our own internal standard? And that was a pivotal moment, right? Because we didn't know if FHIR was going to be the solution, right? It was going to be the last word in interoperability. We thought that, standards, they come and go, right? So we should stay flexible. We should anticipate that newer standards are going to come out, and that we should be able to support it. And so we chose to stay, the conservative choice and stay on our own internal standard, and that was a mistake, right? That we had to pivot away once we realized how big FHIR was going to get in terms of adoption, and sort of the regulations that could come out in that realm. Okay, so let's look at an example of a FHIR server. Right? So this is Epic. They've got a sandbox that you can go register and play around with today, right? So we're looking at the bulk data export, right? So this is how you would get bulk data out of a given EHR. And then if you can see the user types, right? It's only meant for clinicians or administrative users. is not meant for the patient because this is bulk data. You're getting everyone's records, right? As a patient, if you had access to this endpoint, then you could see your neighbor's medical records. So not all resources are meant for patient consumption, but they are there to support research and other population health initiatives. And yeah, you can see basically all the operations, right, and all the resources that you can access. Like care plan, you can read them, you can write them, you can search for them. And the nice thing about FHIR is that all of this is known via a capability statement, which is like an open endpoint, right? It's an endpoint you can just call, and the FHIR server will tell you, these are all the resources that I will support. These are all the operations that you can do, like read, write, search. And your applications, right, it knows the backend that it's talking to. So yeah, having that capability statement is really powerful. That capability statement also describes, right, the methods that you will have to use to authenticate yourself, right? So all of that is standardized, right? You know, as the client trying to get the data, what you have to do. And once you've gotten the data, you know what it looks like. So that's exactly what Apple's done, right? You've got this Apple Health application, right? They can point to any number of EHR, and yet it can display all your medical information, right? And that's because FHIR, right? It knows what the data looks like. FHIR tells the application, as the client, you've got to do this, you've got to make this request in this exact same way, then you can get the data. Okay. And yeah, I guess I'll end with FHIR has certain workflows that are already sort of has opportunities for you to implement AI, right? They didn't really design it for that, but it's kind of obvious that it's that, right? So the first thing that comes to mind would be clinical decision support, right? So that's a FHIR implementation where some clinical expert, right, they define some set of rule with a trigger, a recommendation, and then an action, right? So you've got a trigger if some condition or or lab result comes in, then okay, maybe this is a concern. So I'm going to look up, this observation, J, and then okay, I'm going to recommend Z, Z treatment and K medication, and then the clinician they can accept it and then record the action taken and the feedback. So you've got a complete loop, right? You've got a complete perfect loop. You've got a rule, and then you've got feedback on how what happened whether the rule was followed or they declined it, right? So yeah, this feels like that loop is perfect for training an AI model. You've got FHIR subscriptions, right? So you can subscribe to whenever a resource change. So if you've got some medical decisions made, right, for some patient, and that decision is based on some assumptions or some observation, right? So if those observation changes, then your conclusion will change. So yeah, FHIR subscription would work with that. And clinical quality language, FHIR, right? So that is the expression language for querying, for getting data out of FHIR resources. So it's basically, FHIR, I guess I would describe as sort of semi-structured, right? So 80% of healthcare data is unstructured, so that's your images, your free-form text, medical notes. It doesn't change that. What it does, though, is it puts those unstructured data into specific containers or contexts, right? So, for example, you could have a vector search that looks for the word diabetes, right? But if you don't know the FHIR resource, then you can just think, okay, this shows up a lot. Maybe they have diabetes. But if you're working with FHIR, then you can see that, if diabetes show up in a condition resource, then yeah, they have it. But if it shows up right in a family member history, then they don't. Right? So it just means that they likely would have it. So you kind of combine the unstructured vector search with a structured or semi-structured context that FHIR puts them in. And then bulk data export, right? So you can get population level or cohort level, right? Proof of patient, so that you can study them. Now there's one last one that I didn't put on there, but I'd be remiss not to mention, but prior auth, right? Has anyone heard of prior auth? Yeah. No one likes prior auth, right? You need something done, then you gotta check with the insurance company, they'll pay for it, right? So FHIR has a standard for that now, right? So the insurance companies these days, they're using AI to do that. And well, that's a problem, right? It's not deterministic, right? You have the same request coming in, and you submit the same request identical and then you get a different response, right? So it's not deterministic, it's not an implementation of a policy, right? So FHIR, they've come up with a set of implementation guides that any payer service that provides a Medicaid or Medicare service will have to follow. So it becomes deterministic, right? Basically, if you've got a procedure or a CPAP, for example, right? So you've got sleep apnea, you want surgery. So the provider or doctor, right, they will make a request to the payer, say, okay, I want this surgery, and then right off the bat, the payer side will just send back the discovery document, say, okay, you want that, but you've got to check off these things, right? You have get a sleep study, you have try CPAP machine, right? So then the doctor doesn't have to, look up your medical chart and fill out the form, right? Fill out the application. No, the payer side would use the quality language here in the FHIR path to get that data from you, right? So it's kind of like they're sending you instructions for your system on how to get the data, right? I'm looking for whether you've done sleep study. I'm looking for, try CPAP machine. So yeah, the form is filled out, right? You're not wasting the doctor's time in looking up the chart, filling out the form. So yeah, so there are some places where AI is not appropriate. So you can use AI there, right, in helping craft the FHIR path expression, right, and looking up the data, but using AI, right, to make coverage decision is probably not a well thought out idea. So yeah, I think that's all I've got. Back to you.
Thanks, Steve. I mean, to clarify, we are going to talk about where AI is appropriate, but that is, I agree on that front. So yeah, I mean, Duke has really sort of walked us through, firstly, I mean, the value of EHRs as clinical data repositories, and then the value of FHIR as the data model and sort of the medium of exchange with those systems, right? So we looked a little bit like things like subscriptions and CQL and some of the parts, some of those sort of component parts of FHIR. But what I want to talk about at this point is actually, well, despite having these extremely rich clinical repositories, that doesn't mean you can just use the data, right? So one thing there's this sort of really interesting study. I think some of you might be familiar with this. If you're curious about where HIPAA came from, it was somewhat inspired by this, if not directly. So has anyone heard of Latanya Sweeney? Got no hands? Okay. So she's a computer scientist. She works in the field of anonymized data, specifically looking at how re-identifiable anonymized data is, and it's its own field. So she sort of began her work in the 1990s as a graduate student at MIT, and her particular concern was privacy of medical data. And in 1997, she examined a batch of hospital documents released just for sort of statistical research. And she was able to identify the records of a former governor of Massachusetts. She identified that with just 3 fields: zip code, date of birth, and gender. And in fact, she took this a little bit further, and she actually wrote a paper called Simple Demographics Often Identify People Uniquely. And if you take a look at this last line of section 512, you'll see 87.1% of the population of the United States is likely to be uniquely identified by just their gender, date of birth, and zip code. Right? That's somewhat concerning. In reality, that number is actually 50 to 60%. She made a few assumptions in the calculation. She assumed that every zip code has an equal number of people. Obviously, there are population centers that are more dense than others, so in that case, the number gets skewed a bit. But actually, the calculations are quite simple. If you look at 100 years, there are 36,500 potential birthdays. You look at the number of zip codes in the US, you look at the population, actually, you can sort of follow the calculation through, actually, quite intuitively. So people were obviously slightly shocked by that. As a sort of fun little side thing, she actually has her own website here. Called How Unique Am I? You can actually sort of test this out. If you enter your date of birth, your gender, and your zip code, it will tell you that you're probably the only person in the US with that information. So you might be wondering, what do we do about that? Well, the answer is it's HIPAA, basically. So EHRs are extremely rich in clinical data, authentic patient data, but things like secondary use, things like training an AI application, things like making anything aside from primary care does require consent, and it requires de-identification. And de-identification is not as simple as just scrubbing name and birth date. It's an information science, right? There's a percentage chance of re-identifying anything, and it's just about trying to get that percentage down as low as you can. So HIPAA has something called Safe Harbor. I'm not sure if anyone's familiar with that. They have several guidelines on how you can try to scrub data to basically get this re-identification risk down as low as possible. Recommend you take a look, it's quite interesting. I don't think there's anything on there that's too crazy. But you can even see, it's a little hard to read, but things like distinguishability. One basic thing you can do is try to collect the first 3 digits of a zip code rather than the full 5. Just like that, you go from the 50 to 60% or the 87.1% down to, I think, 0.04% of Americans being re-identifiable, right? So just by cutting that from to a 3-digit collection of zip code rather than the full 5, immediately you drop the risk significantly. GDPR is also similar for anyone that works in sort of the EU space as well, but we'll sort of focus more on the US here. But yeah, the point is de-identification isn't foolproof. So if you want to build something, specifically you want to build maybe an AI application, something that would be subject to secondary usage requirements, you might want to actually look at synthetic patient data rather than authentic. And specifically, I want to talk about sort of 2 approaches to generating synthetic data. I think it's fairly intuitive, but the first option you have is by taking existing clinical data, putting that through a de-identification process, getting that risk score as low as possible, and then using a process called imputation to try to fill in the blanks that you removed. So by using things like probabilistic models, you can generate measures, right, or whatever those might be. You can generate encounters. You can basically start to generate a universe that is clinically plausible, but still not linked to a direct patient or not re-identified. That will preserve real structure. You can have very low risk ratings, and it's very simple to validate the clinical plausibility of that. It's still difficult to de-identify. The second option is basically generating synthetic data from just schemas. So without having that initial EHR export, assuming that the AI models you're using are trained on safe data as well, what you can do is you can basically generate, using generative or tabular AI, incomplete data sets, and then you can sort of validate those as well. The benefit of that is you don't have to go through a de-identification process necessarily. You can manufacture very rare cohorts that may not have existed in your initial data set, but it's much harder to validate clinical plausibility. Right? When you think about the entire sort of care pathway that a patient might go through over decades, it's extremely difficult to sort of build that up from no data at all. I'm going to talk about this very briefly. In terms of some of the methods and tools out there for both of these approaches, honestly, I'd recommend, I'll sort of link all of these articles in the PowerPoint. Definitely, try reading up on some of these if you're interested. There are plenty of generative machine learning models that are trained on de-identified data to begin with. When you sort of combine these with synthetic EHR data from like existing databases, existing research databases, you can get extremely compelling, some clinically valid synthetic data. So using standard libraries in Python or R, for example, you end up with all sorts of built-in libraries that can try to harness this. I'm not an expert on really Bayesian networks or anything. I'd recommend you look that up if you're interested in this particular field. The area that I'm more interested in is complete synthetic generation. So this is when you don't have that initial data set. I think this is an extremely exciting area, not least because we're in the era of generative AI, not just LLMs, but also diffusion models. So healthcare data is extremely complex. You can have imaging data, you can have MRI scans, you can have very complex multidimensional data. Diffusion models are actually getting kind of good at creating synthetic imaging data, synthetic unstructured data. There was a really interesting paper written last year, synthesizing multimodal EHRs via predictive diffusion models. Again, not quite an expert in this, but I'd definitely recommend you take a look. Sort of frontier LLMs, for example, they actually use diffusion models behind the scene most of the time to actually generate images. If you ask ChatGPT, for example, to draw you a picture, it's probably using a diffusion model. Gemini, for example, uses Imagine. And then there are sort of standardized ones like MedGAN that have been used in all sorts of research data sets, and there are lots of sort of models derived from that and fine-tuned from that as well. What's really interesting as well is the usage of agent-based simulations for care pathways. So if you're familiar with sort of agentic AI frameworks, you might imagine that actually, if you really want to simulate not just one patient, but maybe an entire cohort of patients moving through, effectively a whole series of encounters and care services and practitioners, you can actually use things like agentic AI to try to simulate those encounters and try to really build up that data set in a very sort of unique and sort of quite intelligent way. In terms of how relevant is this, it's extremely relevant. I think for those of you that follow the analysts, for example, you may have seen this. This graph's actually a few years old now, and I think it's probably maybe underestimating that there isn't really a y-axis here. But the point is, synthetic data is going to be used a lot more than authentic data in terms of training AI models going forward. We've sort of reached a point where AI models are intelligent enough, and we have the right kind of infrastructure to support this. We can end up with extremely sort of exotic, well-formed clinical repositories using really not much authentic data at all. Yep. So within the context of FHIR specifically, I'm not sure if any of you have attended NHL7 Connectathon or any of the working group meetings. For those of you that have, there was a meeting last week in Pittsburgh. There are now several working groups working directly in terms of sort of AI identifiability of data. So this isn't necessarily how do we use AI, to improve care outcomes. This is more about how do we trace the impact of AI through our health system. So if I'm using any of these models to actually generate these synthetic cohorts, how do I actually tag that data safely so that people know where it came from? How do we create the right metadata for people to identify this stuff? It's a really interesting area, and it's also being developed. Is anyone here familiar with Cynthia? Yeah, I've got a couple of hands. Okay. It's actually being developed by a lot of the same people that worked on Cynthia. So Nita, the corporation, they're sort of leading a lot of these efforts. But yeah, we've got sort of informaticists and researchers working directly to try to identify sort of a long-term strategy for identifying sort of the prolific AI data, AI-generated data. And for me, I'm kind of wondering, do they know something we don't? Is there already sort of huge amounts of AI-generated clinical data bumping through these systems, or are they just sort of ahead of the curve on this? I'm not entirely sure. Hopefully the latter, but we'll see. And then that sort of brings us to section 3, which is about safety and bias. So we've kind of established the EHRs are the repository of choice for really any kind of clinical application or healthcare administrative application. Talks a little bit about limitations in using authentic data and the need for synthetic data sets. And now I want to talk about safety and bias. So, who here has suspicions that healthcare AI might be slightly biased? Yeah, you're right. So, pretty consistently, before generative AI as well, any kind of AI that's been generated on public research data sets, some of the largest data sets have consistently found racial bias. For example, there's been gender bias as well. A lot of the reasons for this come down to basically incomplete data within a lot of these research sets, just sort of poor coverage, sort of a general lack of sort of what we call data fidelity, which is how completely does the data describe the population we want to study. So this actual article up here was actually published last week. AI medical tools found to downplay symptoms of women and minorities. This is an LLM-based application where they found that the LLMs were creating inferior medical advice for female Black and Asian patients. When you think about it, it's not just the data that is being trained on, it's also bias of clinicians who helped to train the models. When you think about responses that may have been given, case studies that were part of the training, there's actually, how do we try to ensure that these models aren't effectively internalizing any bias that already exists within the healthcare provider space, within any given set of practitioners? And how do we try to identify that? So there's not really a straightforward answer to this, but there's more a set of things that we can try to consider. So when we talk about AI pipelines, we're really thinking about the end-to-end process of retrieving this data, building a model on it, and then trying to deploy it. So the first thing to look at is data fidelity in synthetic or authentic sources. There are a few papers on this, but sorry, I meant to sort of expand the key down there. It's kind of hard to read. Hopefully you're not colorblind, but in dark blue, we have basically the breakdown for synthetic data that's being used for these AI applications. You can see it ranks highly in terms of data fidelity, that's sort of the completeness. It ranks obviously extremely well for patient privacy, that is synthetic, but also extremely well in terms of utility. So there is sort of a trade-off that first needs to be considered between synthetic, partial synthetic and truly authentic data in terms of privacy, fidelity, and then utility. In particular, let me just double check. Yeah, so anonymized data, for example, ranks extremely poorly. That's the green triangle in terms of privacy, but it's generally highly useful. I think this diagram is maybe somewhat debatable, but just to sort of give you an idea of maybe the three axioms that you first want to consider, also the three measures that you want to consider with your data set, this might be a good starting point. And then we start to look more at how do we then distinguish between subgroups of that population, so whether it's authentic or synthetic. There's some really interesting results here where people have found that by taking research data sets, I think in this case they were looking at UK Biobank, Columbia University data set, and a data set produced by CDAR-SEMI. They found that when they tried to enforce data quality rules on this data set before training an AI model, those data quality rules actually exclude a lot of data belonging to ethnic minorities disproportionately. So by actually enforcing certain, I think they had sort of 19 or so commonly used data filters on this set, and they found that consistently they were seeing clinical data completely excluded because it didn't match certain completeness requirements, it didn't match certain timelines, it was just missing certain data. And of course the result for that is you get more bias. You have data that is being excluded for patient populations simply on the basis of the fact that that data wasn't collected in a certain way, it wasn't produced in a certain way, it wasn't cleaned in a certain way. They found that their results are here. Among those examined, the availability of data in the white group remained consistently higher compared to other racial groups after applying each filter. So you can imagine that even with intentions of improving data quality, you do also run the risk of discriminating against certain care groups. Again, it's how do we try to identify sort of the shape and some of the risks to these data sets. And one sort of interesting, for those of you that sort of worked in the ML space, this might look somewhat familiar, the concept of counterfactuals. This is kind of an interesting way of trying to interpret an AI model's actions. Right? The idea being, if I change one demographic, if I change one feature, does that change the clinical decision being made? So I have case studies here about loan approvals, for example. If I have an AI model that either approves or rejects some kind of loan, I might first provide it some data. I might give it data for, I'm not sure, maybe, I think I've got an example here. Yeah, 22-year-old, high school grad, single white female, right? According to the AI model here, it's this line here, you can see that they're rejected for the loan. That's what this, it's a little hard to read. You can see here it says query instance original outcome 0, that means they were rejected for the loan. So what you might want to do is say, if I start modifying some of these fields, how does that impact the approval or rejection of the limb? So there are Python libraries that actually do this. If you identify which features you want to test against, what it will do is it will modify some of these initial parameters. It might modify how the application basically invokes the LLM, and it will try to see if that modifies the actual class output. Will that then move somebody from approved to rejected? So actually what we see here from this Python application is they have a whole list of sort of counterfactual data sets that were approved when they started modifying the data. In this case, they're not super closely related to the initial applicant here, but you can see a 70-year-old, 70-year-olds, any gender with a master's degree, white-collar occupation does get approved. We can see self-employed, no age given with a doctorate, and married does get approved. You can start to see how we can start using this counterfactual analysis to manipulate some of these demographics and try to figure out, are we seeing consistent approvals or rejections? Are we seeing consistent clinical decisions being made on a single parameter? I'd recommend taking a look. There are actually open source libraries here. Some of them produced by Microsoft, and I think there's sort of a larger open source community here that tries to build these sort of counterfactual frameworks. But it's sort of a really interesting way of testing a model that has been trained, trying to really, trying to sort of expose and interpret some of its actions. And then I kind of want to wrap this back up. So the theme of this talk is FHIR, and we haven't necessarily talked about FHIR a huge amount. FHIR is sort of acting underneath the surface with all of this. In particular, looking back on 2025, for example, we are seeing a huge surge in generative AI applications being deployed at healthcare providers. We've seen sort of projects like Chat EHR at Stanford Health, for example, where they're using EHR data and they're using LLMs and they're using AI systems to actually triage patients in the emergency department. We're also seeing a huge push in terms of medical device interoperability. That's kind of the second theme I want to look at. So things like wearables, remote monitoring. We're seeing, obviously 5G hospitals have been around for a few years, but coming out of COVID in particular, remote monitoring is becoming sort of a huge focal point. And then we've got to think about who has access to that care. And then we're also seeing just sort of health exchange exploding in general. So here we've got sort of a particularly impressive achievement. We've got Indian Health Service onboarded into TEFCA. Is anyone familiar with TEFCA? Network of networks, trust, So, Indian Health Service is onboarded with the eHealth Exchange. That's one of the health information networks. And so we're seeing this sort of nationwide push for interoperability. So I'm just going to just the summary here in terms of what I just talked about. In particular, seeing federal partners on board too, QNs is, I think, a real push in the right direction in terms of, especially for sort of improving access to care and obviously having, improved studies on population health. But what kind of ties this all together is actually FHIR. So consistently with any of these interoperability programs, with a lot of these sort of AI applications, FHIR is now becoming not just the language of choice, but really the only language that's capable of supporting all of these use cases. It is by far sort of the most advanced and sort of developer appropriate set of APIs and data model that's really going to enable this kind of development. We're extremely excited to see where this goes, but somewhat cautious about how it gets implemented. So that's everything I wanted to cover. Thank you very much.